Hello engineers, welcome to the new video of the course, and in this particular video we are going to understand the drawback of the circuit which we had deduced in our previous session. But before going to that particular topic, we'll just quickly revise what all things we had seen in our previous video. So in the previous video we saw that I had considered this source as a heart, right? And when I talk about source, so I should also be talking about the source resistance because that also plays an important role, right? And obviously the source resistance would be in series with the source voltage, right? And I'm providing this particular signal to the system 2, and my system 2 is an amplifier, right? And we all know amplifier has its own input impedance, right? So this is an input impedance of an amplifier. But when I'm saying this particular resistor or R2 with respect to heart or with respect to source, so this R2 will act as a load resistor or load impedance with respect to heart, right? Great. So now let's proceed further. We'll focus on this particular circuit only. Alright. So you can clearly see, and the entire circuit is same. Just the thing is that I had assigned certain values to R1 and R2, right? So let me just give you a rough idea. So when you design any amplifier, you design it based on the signal which is coming from the source, right? Okay. And no matter what, you try to keep the input impedance of any amplifier as high as possible, right? So that means what? This R2 should be much more greater than R1. Okay, because your R1 is source resistance, whereas your R1 is source resistance, whereas your R2 is your load impedance or load resistor, right? So you try to keep this particular R2 much greater than your source resistance, right? And that's what I had done over here. Okay, I had just taken a rough value for R1, which is around 2.2 kilo ohm, and then I had multiplied it with 2. So this pans out to be around 4.5, something like that, but I had considered this value as around 4.7 kilo ohm. Okay, if you want, you can take R1 as 5 kilo ohm and R2 as around 10 kilo ohm, something like that, 10, 11 or 13 kilo ohms. It totally depends on you, but make sure that R2 should be greater than R1. Okay. But you know, in practical scenarios, generally this particular value R1, it would be around 100 to 500 ohms or even less than that. Okay, because it is in few ohms. If you try to calculate the resistance of your heart, it might be in few ohms only. That means 100 to 500 ohms. Okay, but just for simplicity purpose, I had considered the value of around 2 kilo ohms, which is around 2.2 kilo ohms. Okay, and that's why if I multiply it with 2, I'll get the I had taken the value for the load resistor, that is R2. Okay, just for calculation purpose only. Okay, otherwise in most of the practical scenarios you will find this value to be quite smaller, mostly in the range of 100 to 500 ohms, surely not more than that. Okay, great. So now let's proceed further, and then we'll try to analyze what is the drawback of this particular circuit. But before moving further, let me ask you this particular question, that can you guess this particular circuit? It's quite simple. You can easily guess this particular circuit because we had done lots of numericals. We had also done lots of project with the help of BJTs by using this particular circuit. I know most of the students might find it little tedious to guess this particular circuit. So what I'll do, I'll rearrange this particular circuit, and after rearranging this particular circuit, it will look something like this. And I believe that now you are in this particular situation to guess this particular circuit properly. Well, this is a voltage divider circuit. I hope you are able to recollect what we had studied in our previous few videos. See, the circuit is same. I just rearranged this particular circuit. It was in horizontal way. I just arranged it vertically. So basically, I am interested to know what voltage I am getting at this particular point. What voltage I am getting at this particular point. Okay, if this particular point or if this particular node gets an adequate amount of voltage, then only whatever the amplifier that is present, it would be able to amplify this particular signal properly. Okay, so for that we need to make sure that whatever the signal that is coming over here, it should be as high as possible. Okay, so this is what we need to find out. Okay, let me erase it. All right, now what I will do, I'll just apply the voltage divider formula. Okay, so therefore this V out would be, I hope you all guys are familiar with the formula which we had already seen in our previous few videos, right? V out would be equivalent to Vs, okay, that is the source voltage, into R2. R2 is nothing but 4.7K divided by 2.2 plus of 4.7. 2.2 plus of 4.7. I'm not writing kilo ohm because any which ways, if you write K ohm, so it is present in both denominator and in numerator. So any which ways it is going to get cancelled, right? So let me just calculate this particular value by putting it in calculator. So it is 4.7 divided by 2.2 plus of 4.7. So this value pans out to be around 0.681. Okay, I'll consider this particular value to be around 0.68 only. So therefore my V out would be equivalent to 0.68 times of the input signal. 0.68 times the input signal. Now what does that means? What does that means? Let me just highlight this particular point. That means what? See, let me just come to this particular diagram. Okay, I had written over here. That means what? My source, okay, my system 1 or my source, it is providing 100% signal from its side, right? That means what? My source is providing 100% of signal, right? But when this particular signal, it is coming to the amplifier part, the amplifier is only getting 68% of the signal, right? That means we are losing around 32% of the signal, or 32% of the signal is acting as a loss signal, right? That means what? Let me just write over here. 38% of the signal is being lost. Loss of 38% of signal, loss of 38% of signal, right? Or rather 38% of the signal, it is getting reflected back to the source. I can also write it in this way. So this particular 38% of the signal, it is getting reflected to the source once again. Reflected to the source. Reflected to the source. That means what? We are just getting around 68 to 70% of the signal to the amplifier side, right? And then even though amplifier will perform the amplification by certain factor, but still we won't be getting the desired signal at the maybe at the system 3 or whatever that particular system is, which is present after amplifier. Okay, so that's the biggest drawback. I hope you are able to understand what I'm trying to convey to you all guys. Again, I'll repeat. See, I had taken some random number, okay, for this particular two resistors, okay, and then obviously I'm going to perform the voltage divider rule or voltage divider bias technique, and with that I got certain value for V out. With this value, what we saw or what we can conclude is that whatever the voltage that we are getting at this particular point, that is at this particular point, okay, that is 68%. Let me change the color. That is roughly around 68% of the original signal. That means 32% of the signal is being reflected back to the 32% of the signal is being reflected back to the source, or rather there is a loss of 32% of the signal, right? I hope you are able to understand this particular part. Great. So for that, to counter this particular issue, okay, to ensure that whatever the signal that we are feeding to the amplifier, or rather that this particular source is delivering to the amplifier, it should be getting reflected as it is to the amplifier. We need to design one system in between both of this particular resistor, which will ensure that whatever the signal that it is getting, the same signal would be reflected over here. What I mean to say is this. Just a second, let me proceed further. See, what I mean to say is this. That means what? Whatever the signal, no matter what that signal would be, whatever the signal that is being generated by this particular source, so this particular system which we will be designing, so this system should take this particular signal, and this particular signal will this particular system should reflect this particular signal as it is over here, okay, to the input of this particular amplifier. Okay, I hope you are getting this particular point. That means what? We are basically avoiding this particular voltage divider rule and all. Okay, for that we are we had designed one system which ensures that whatever the signal that is being delivered by this particular source, okay, that is our hard or source, whatever it may be, hard or source, so same signal should get reflected to the system 2, that is our amplifier. Great. And it can only be done with the help of buffer amplifier. It can only be done with the help of buffer amplifier. Okay, so you can clearly see this was our heart. Again, I'm writing it again and again so that you should be able to understand what I want to convey to you all guys. This is my heart or source, and this is my amplifier, right? This is my amplifier, and in between we need to connect one amplifier that is known as buffer amplifier. Buffer amplifier. And I hope that you understood why the gain of buffer amplifier is 1, because see what amplifier does. Okay, what amplifier does, it just amplifies the signal, right? If the amplification factor of any amplifier is 100, so it will multiply that particular signal by 100. Okay, it will increase its voltage gain, right? Now in case of buffer amplifier, the gain is of 1, right? So over here, if it is getting the signal of X over here, and the gain of buffer amplifier, let's suppose it is 1, so G times of X. So at the output side you will get the signal as G times of X. Our G is 1, so 1 into X is nothing but X only. That means what? Whatever the signal that we are feeding to the input of buffer amplifier, the same signal is being delivered by the buffer amplifier. I hope you are crystal clear. And one more thing I would like to add over here, that the input impedance of buffer amplifier is quite high. Let me change the color just a second. Yeah, the input impedance of buffer amplifier, the input impedance of buffer amplifier is very high, whereas the output impedance of buffer amplifier is very less, and with this particular property only, it is being able to deliver the signal which is being fetched by the source to the amplifier. Okay, so I hope you understood what is buffer amplifier. I know like you don't understand it properly because we had not deal with the buffer amplifier in detailed way, but at least you got a brief idea of what exactly a buffer amplifier is. So let me just repeat what all things we had done. See, I had considered the values for this particular R1 and R2, and when we try to apply the voltage divider rule for it, what we got was this, that is my V out. It is 68% of the original signal. That means what? Whatever the signal that is being delivered over here, it is just 68% of the original signal which is being delivered by the source. That means there is loss of around 32% of the signal, or that particular signal is getting reflected back to the source only, right? So to counter this particular issue, we need to design one system in between. So this particular system, what it will do, it will reflect or it will deliver whatever the signal it will get at its input side, right? And this particular system 3 or this particular system is nothing but your buffer amplifier. This particular system is nothing but buffer amplifier. So let me proceed further. Yeah, and as I told to you, even most of the students they know that the buffer amplifier provides unity gain. That means its gain is always 1, right? And you can clearly look over here, if its gain is 1, so whatever the signal that it is getting at the input side, so it will multiply it with the factor of G is nothing but 1. So same signal would be reflected at the output side of the buffer amplifier. Okay, and this is just you just remember this particular point, that the input impedance of buffer amplifier is very high, whereas its output impedance is very less. Don't worry about this particular part. We are going to analyze this particular concept of impedance, that is input and output impedance of buffer amplifier, in depth when we will try to analyze this particular buffer amplifier by taking certain circuits, right? So don't worry about that particular part. Okay, but I really hope that you understood this particular concept of buffer amplifier. At least you got a basic idea. Okay, great. So now what we will do in the next video, we will simulate the circuit. We will simulate the same circuit. See this one, not this one. Yeah, we'll simulate the same circuit. Okay, by taking Vs as around 1 volt peak to peak. So in that particular simulation, what we will do is that we will take Vs as 1 volt peak to peak. So that would be our peak to peak voltage. I know that the signal delivered by the heart, it would be in few millivolts, right? Precisely it is around 1 millivolts, right? But For simplicity purpose, again I'm telling for simplicity purpose and to make the calculation pretty easier, we'll take the random values which is quite easy to calculate, right? Which would be quite easy for calculation, right? So that's why we'll take value of Vs as around 1 volt peak to peak, right? We'll keep the value of R1 as around 2.2k and R2 as around 4.7k, and then we'll check over here that we are getting whatever the signal that we are getting over here, is it 68% of the original signal or not? Okay, great. Yeah, so this is my Vs, right? This is my R1, that is 2.2 kilo ohm, and this is my R2, that is 4.7 kilo ohm. Great. I hope this everything is visible to you all guys. Let me erase all of the things now. Great. And now what I'll do, I'll just run this particular circuit because I had already set the things, that is I had already set this particular signal as around 1 volt peak to peak, and then we'll check what signal we are getting at this particular point. Okay, and I believe that you all guys are familiar with the Proteus software. You all guys know how to use this particular software because in almost, I guess, 2-3 courses I had covered this particular software in depth. Okay, so anyways, we'll start, or rather we'll simulate this particular circuit and we will check what what kind of signal we get over here. Okay, so let me just run this particular circuit. All right, so before coming to this particular part, let me just show it to you so you can clearly see the input signal. It is of 1 volt peak to peak, right? As I had mentioned over here, 1 volt peak to peak, and frequency I had kept it as around 100 hertz. Okay, because frequency of that I guess ECG or heart signal, it is around 70 to 100 hertz, something like that. I'm not that much sure, but any which ways, for this particular practical scenario, you take any value of frequency. As of now, that's not a big concern for us. What we need to check is this, that is the voltage that we would be getting. Okay, so you can clearly check over here. See this particular part, this particular A, that is this particular yellow color wire I had joined to the input side, right? Yellow color wire I had joined to the input side, and this is where my signal is being generated. So this is my Vs source. Okay, that is being represented with the yellow color. Okay, and output I am seeing with the help of the blue color, that is B. You can clearly see the blue color is being represented with the B, and I had connected across 4.7k, which is the output, right? So first of all, let's check whether we are able to get the 1 volt peak to peak signal. That means 500 millivolts up and 500 millivolts down, right? And when we subtract them, we will get 1 volt peak to peak, right? So let me check if we are able to get 1 volt peak to peak signal. Yeah, so this is 500 millivolts up and this is 500 millivolts down. You can clearly see over here. So when we subtract both of them, we'll get 1 volt peak to peak. That is, although I had explained you this particular part, but still, just for your better understanding, I will explain you this particular part one more time. Alright, so you can clearly see over here, this is 500 millivolts, right? And then we need to subtract this with this one. Just a second, let me erase this part. I will write over here. So this is 500 millivolts, 500 millivolts. That means this part. And then we have to subtract this one, minus 500 millivolts. Sorry, minus, just a second, minus 500 millivolts, right? And when you subtract them, you will get 1 volt peak to peak, or 1000 millivolts peak to peak, which is eventually 1 volt peak to peak, right? 1 volt peak to peak voltage. Okay, so this is what we had given at the input side. Now let's check the output, because for us the output matters a lot. That means output should be 68% of the input signal. My input signal is how much? 1000 volts peak to peak. So let me just calculate over here very quickly. My input is how much? 1000 millivolts peak to peak, or 1 volt peak to peak, right? Peak to peak, or I can also write it as 1 volts peak to peak, right? So 68% of this particular signal, right? 68, that means 68 by 100 into 1000. So it pans out to be around 680 millivolts, right? 68. I hope you are quite good in mathematics. I'm not doing each and everything over here, but 68 by 100, 68 divided by 100 into this value, that is 1000, or 1 volt peak to peak, right? But since it is in millivolts, so obviously we need to take 1000, right? So you can clearly see this 0 and this 0, they are getting cancelled, and what we have is this, that is 1000 millivolts, right? So over here this was 1000 millivolts, right? So this is around 680 millivolts peak to peak value, peak to peak value, peak to peak value. Again I will repeat. See, just a second, let me give a moment to erase all of the thing so that I can show it properly. See, so output should be, according to our calculation, it should be 68% of the input signal. So 68%, that means 68 divided by 100 times of what is our input signal, what is our Vs. You can clearly see over here it was 68% of, or 0.68 times of Vs, right? So what is our Vs? Again I'll write it over here, sorry for that, just a moment, give me a moment. Yeah, so write it again. I know it is taking time a bit, but your concept should be pretty clear, right? So it is 1000 millivolts peak to peak or 1 volt peak to peak, right? It's one and the same. And our output should be 0.68 time or 68% of the input signal. So 0.68 or 68% of input signal. My input is 1000 millivolts peak to peak, so it would be around 680 millivolts peak to peak signal, That means what? The entire signal from here to here, it should be of around 680 millivolts peak to peak. Okay, or what is half of 680? So it should be around from the above peak should be around half of this is around, half of it is 340. Yeah, 340 up and 340 down, right? And eventually when you subtract both of them, you will get what? You will get 680 millivolts peak to peak. Okay, so let's check if we are getting 340 millivolts up and down. So let's check that. Let me erase all of the thing. Okay, great. So now let me take this cursor and let me just a second. Yeah, let me just yeah, you can clearly see it is 340 millivolts up, and let me just click over here. When it detects this, yeah, it is minus 340 millivolts down. And now you can clearly see when we subtract both of them, so we will get what? We will get 680 millivolts peak to peak signal. That means what? It's absolutely working fine as we concluded. That means what? Let me write over here as well. Just a second. Yeah, let me just write over here. That means over here we are providing 1000 millivolts peak to peak signal or 1 volt of signal, 1 volt peak to peak signal, and over here we are getting 680 millivolts, 680 millivolts peak to peak signal or 0.68 times of the 1 volt. Okay, that means 0.68 volts peak to peak, obviously. Okay, so I hope that you understood what I wanted to conclude to you all guys. That is, when we are connecting this particular circuit in this way, right? When we are connecting this particular circuit in this way, so this is what we get. That means it is eventually, although we are not forming the voltage divider, this voltage divider circuit intentionally, but somehow it is getting formed, right? Somehow it is getting formed. Okay, and based on this particular logic only, we deduce that 0.68 times of the input signal we would be getting at the across the load, that is 4.7 kilo ohms, whereas the remaining 32% of the signal or 0.32 times of the input signal, it would be lost, right? Or rather, I think it would be getting reflected back to the source side only. Okay, as of now we don't want to go in that particular part, but want to remember over here is that some amount of the signal is being dropped, okay, over here, whereas some amount of the signal is being lost. Okay, so to counter this particular issue, what we do, we connect a buffer amplifier in between both of this particular resistor so that it can counter this particular issue. Okay, so I really hope that you understood the simulation which I had done over here practically. Okay, but still, if you have any doubts, if you are facing any difficulties, you make sure to ask me in the comment section. Okay, so thank you for listening patiently. I'm ending this video over here, and in the next video, and from the next video onwards, what we'll do, we will try to design this particular buffer amplifier with the help of transistor. Okay, that is BJT, bipolar junction transistor, BC547. Okay, thank you.